2029, a new spacecraft will rise from Earth, carrying with it not just instruments of science, but the legacy of one man's 30-year struggle for knowledge. This mission is not an ordinary voyage. It will carry embedded artificial intelligence, predictive radar, autonomous navigation, and self-healing power systems, technologies that will enable the spacecraft to operate independently in deep space, anticipate challenges before they arise, and adapt to the unknown.
This mission is needed because space is not just a frontier, it is a hostile wilderness. Communication delays, cosmic radiation, power instabilities, and jamming threats mean that future spacecraft must think for themselves. They must not wait for commands from Earth, they must anticipate, decide, and act. This 2029 spacecraft will be one of the first to demonstrate such true autonomy in orbit.
But behind this historic mission lies a story of dedication that began far away from the launch pads of America. It began in Pakistan, where a young scientist, Adnan Zaidi, dared to dream of systems that could survive in the harshest conditions, under the ocean, in the skies, and eventually in space.
For more than 3 decades, from 1997 to 2025, Zaidi worked tirelessly, producing breakthrough after breakthrough in submarine control logic, avionics, radar, artificial intelligence, and system-on-chip architectures. Step by step, he built the knowledge base that would one day converge into the technologies destined for NASA's 2029 mission.
By 2025, he entered the final stages of his preparation, refining models, unifying architectures, and creating chip-based solutions that could withstand the unforgiving realities of deep space. These last 4 years, from 2025 to 2029, are not just the conclusion of a research project, they are the culmination of a lifetime of vision.
What makes this story even more extraordinary is its origin. That a scientist from a developing country like Pakistan could sustain such a journey across continents, across decades, is nothing short of a miracle. And yet, it happened. American, Canadian, and European scientists have welcomed him, celebrating his 30 years of effort, and recognizing his work as a contribution not just to one nation, but to the collective progress of humanity.
And so, before the spacecraft lifts into the heavens, let us look back. Let us see how one man's 30-year odyssey, against all odds, has led to this moment.
This is the research journey of Adnan Zaidi. From 1997 to 2025, a scientist whose vision now carries us toward the stars.
In the late 20th century, amidst the bustling streets of Pakistan, a young scientist named Adnan Zaidi began a journey that would span continents and decades. His story is not one of sudden breakthroughs, but of relentless perseverance, meticulous research, and visionary thinking. From 1997 onwards, Zaidi's work bridged the worlds of aeronautics, naval defense, smart grids, and artificial intelligence, each contribution building toward a dream that would one day take shape as a NASA space mission in 2029.
This is the chronicle of his scientific odyssey. 1997, Foundations in Submarine and Power Systems.
The year 1997 marked the beginning. Zaidi's first explorations focused on submarine control logic systems. In particular, he designed MESMA-based air-independent propulsion control frameworks for the Agosta 90B submarines. These early contributions were crucial to naval endurance and stealth, reducing dependency on surfacing for oxygen supply.
Alongside this, Zaidi introduced an adaptive neurologic approach for load balancing in power substations. At a time when artificial intelligence was only just entering engineering applications, this foresight illustrated his ability to merge computing with electrical resilience. These studies foreshadowed the cyber-physical integration that would later dominate 21st century aerospace and space systems. 1998-1999. From fiber optics to radar modernization.
In 1998, his research turned toward fiber optic communication for naval platforms, ensuring data integrity aboard legacy Type 21 warships. This work combined classical communication theory with emerging optical technologies, guaranteeing robustness under electromagnetic stress and marine combat conditions.
By 1999, Zaidi pivoted to radar and sonar modernization for Mirage fighters and Agosta submarines. His designs leveraged wavelet-based fault isolation, embedding digital signal processors for real-time naval smart substations. These advances weren't merely military, they were stepping stones towards systems that could withstand the complexity of aerospace missions. 2000. Hybrid AI for grids and submarine navigation.
At the dawn of a new millennium, Zaidi expanded into hybrid AI-based stabilization for islanded microgrids. He proposed using neural fuzzy combinations to ensure stability in isolated energy systems, ideas that would later underpin both terrestrial microgrids and extraterrestrial habitats.
Simultaneously, his work in subsurface navigation for Agosta submarines combined countermeasure electronics with stealth positioning. This dual focus, grid resilience on Earth, and deep navigation under hostile conditions foreshadowed his lifelong pursuit of cross-domain adaptability, equally applicable beneath oceans or in outer space. 2001-2002. GPS fusion, fire control, and smart load management.
By 2001, Zaidi ventured into GPSN's fusion for avionics platforms, enhancing fire control logic for fighter jets like the F-7PG, as well as integration with Harpoon missile systems. These studies represented his first strides into fighter avionics, where synchronization between navigation and weapons demanded flawless reliability.
At the same time, he proposed self-healing networks for urban grids, an early articulation of the concept that power systems should recover autonomously after faults, a precursor to autonomous spacecraft subsystems.
In 2002, Zaidi extended his research into radar warning receivers and AIP power management for multi-domain combat. Equally significant was his work on neural fuzzy coordination in tactical microgrids and ANN-based smart load shedding for industrial grids. These solutions merged AI with decision-making at the system level, preparing the foundation for AI-managed spacecraft power systems. 2003-2004, avionics displays, reconfiguration, and swarm AI.
2003 brought forward breakthroughs in avionics display systems and GPS route optimization for multi-platform combat operations. This marked a shift toward human-machine interaction, where pilots could rely on intelligent display aids in fast-evolving battlefields.
The same year, Zaidi explored dynamic reconfiguration of aircraft electrical networks, using decision tree algorithms to sustain operations in emergencies. In parallel, his research in transformer fault localization via embedded real-time processors highlighted his obsession with system survivability.
By 2004, Zaidi's interests embraced swarm intelligence for emergency grid control. He envisioned distributed AI agents capable of reorganizing electrical flows during crises, a principle that would later influence both UAV swarm control and satellite constellation management. 2005, DSP and UAV microgrids.
In 2005, Zaidi concentrated on integrated DSPGA control for harmonic reduction in rural grids, balancing power quality through hybrid signal processing and genetic algorithms. His parallel research in real-time short-circuit classification for UAV-based microgrids extended these ideas into aerial energy systems.
Here, the trajectory was unmistakable. From naval platforms to airborne microgrids, Zaidi was envisioning a multi-domain architecture of resilience, where aircraft, ships, and ground systems all shared a common AI-driven backbone. From 1997 to 2005, Adnan Zaidi stitched together innovations across naval defense, fighter avionics, grid intelligence, and early AI control. What emerged was not a scattered career, but a progressive layering of technologies, each designed to make systems smarter, more autonomous, and more survivable.
The seeds were planted, and in the coming decade, his journey would accelerate toward reinforcement learning, SoC design, and predictive avionics, bringing him ever closer to the vision of a spacecraft that could navigate, decide, and endure far beyond Earth.
PHS utbevt at the power soaring. 2006, fly-by-wire and space microgrids.
By 2006, Adnan Zaidi had begun shifting his lens toward the future of aerospace and space systems. His research into early fly-by-wire architectures for lightweight fighters introduced stability augmentation and digital control far more advanced than mechanical predecessors. Parallel to this, he developed fault-tolerant energy routing for space microgrids using SVM-based AI models.
At a time when outer space research was still cautious about deploying autonomous AI in orbit, Zaidi envisioned grids in extraterrestrial habitats that could self-correct and reroute power, much as they would on Earth. This dual line of work, fighter avionics and space grids, would become the heartbeat of his career. 2007. Avionics interfaces and reinforcement learning.
2007 brought decisive strides in combat avionics integration. Zaidi contributed to the JF-17 fighter's interface design and worked on C4ISR integration for the F-22P frigates. By By linking command, control, communications, and intelligence into a seamless framework, he was helping craft systems that could think together across air and sea.
The same year, he pioneered adaptive reinforcement-based controllers for airborne power switching. This was one of his earliest forays into reinforcement learning, long before it became fashionable in AI. By applying it to power routing in the sky, Zaidi anticipated decades of research that would culminate in autonomous aircraft and spacecraft. 2008-2009, radar optimization and embedded systems.
By 2008, Zaidi advanced into radar waveform optimization for the JF-17 fighter and guided missile control for F-22P frigates. His work blended digital signal theory with adaptive AI, ensuring radar clarity under jamming conditions, a theme that would reappear in his anti-jamming systems a decade later.
2009 marked his entrance into embedded system-on-chip SoC design for urban transformers, alongside software-defined targeting in F-16 fighters. These two threads, SoC hardware miniaturization and adaptive targeting, foreshadowed his eventual dream, spacecraft that could autonomously reconfigure their power, radar, and navigation systems in the void of space. 2010, fault-tolerant avionics.
In 2010, Zaidi worked on fault-tolerant avionics in the F-16 Block 52, integrating fiber optic bus systems into naval frigates. His designs guaranteed survivability when electrical or computational failures threatened mission continuity. Alongside this, he crafted multi-resolution neural classifiers for tactical grids, giving power networks the intelligence to categorize and adapt to faults instantly.
These ideas mirrored biological systems, just as the human brain filters signals across resolutions. His grids filtered data to maintain operational clarity. 2011-2012, RF filters, AESA radars, and microgrids.
In 2011, Zaidi delved into RF filtering in tactical jet avionics and fire control systems and frigate platforms. These efforts ensured speed, precision, and survivability under radar saturation. He simultaneously developed deep learning adaptive relays for underground networks, a testament to his foresight in applying neural architectures to mission-critical infrastructure.
The following year, 2012, marked a pivotal moment. His proposals for low-cost AESA radar systems for lightweight fighters and rotor-linked sonar processing for naval helicopters. These studies democratized access to advanced sensing, proving that even compact platforms could carry intelligent radar. At the same time, he published on AI-enhanced microgrid autonomy in military outposts, small-scale, self-sufficient grids that prefigured how astronauts might one day power their stations on Mars. 2013, digital avionics and neural MPC.
By 2013, Zaidi introduced digital avionics architectures for the JF-17 Block 2 and low-noise signal enhancement for ASW helicopters. This body of work epitomized his vision: lightweight platforms carrying advanced digital systems, resilient under noise and interference.
Equally important was his exploration of transformerless power management using embedded MPC neural blocks. He was now blending model predictive control with neural networks, a hybrid that would resurface in his later PNN MPC framework for spacecraft in the 2020s. 2014, Deep Cortex and Embedded GNNs.
In 2014, Zaidi unveiled Deep Cortex, a deep neural network algorithm for context-aware pattern recognition across distributed systems. It represented his recognition that pattern detection is the foundation of autonomy, whether in an aircraft, a submarine, or a satellite.
He also pioneered embedded graph neural networks for shipboard load prediction, foreshadowing the GNN-based solutions he would later propose for interplanetary power routing. With Deep Cortex, he entered the frontier of deep learning. With embedded GNNs, he mapped the road to intelligent distributed control. 2015, DNN, Predictive Diagnostics and Hypersonic Aircraft.
2015 was a watershed. Zaidi published on deep neural network-based predictive fault diagnostics and adaptive power management for integrated avionics electrical systems in combat aircraft. This meant not only could aircraft detect their faults early, but they could manage power proactively in real time.
In parallel, he explored multi-agent AI for electric load sharing in hypersonic aircraft. This was the beginning of his engagement with hypersonic systems, platforms that demanded unprecedented speed, resilience, and autonomy. His algorithms ensured that, at Mach speeds, power distribution could adapt instantaneously to dynamic stress. In ORS, from 2006 to 2015, Adnan Zaidi's work evolved from fly-by-wire fighters and radar optimization to to deep learning architectures and SoC design. What began as enhancements for defense platforms had now matured into a unified vision of autonomy. Aircraft, submarines, and grids could all adapt, heal, and survive under hostile conditions.
The stage was set. In the decade to follow, Zaidi would push further into AI radar filtering, anti-jamming navigation, federated learning, and cross-domain SoC architectures. And all of it would converge on a singular horizon, a 2029 spacecraft mission under NASA, shaped by nearly 3 decades of relentless innovation.
Hostum free AI radar target filtering and naval threat modeling.
By 2016, Zaidi had turned his attention to the emerging threats of radar clutter and electronic warfare. His research on AI-based radar target filtering in JF-17 fighters demonstrated how neural algorithms could distinguish genuine signals from decoys in split seconds. He paired this with intelligent threat modeling in naval craft, ensuring surface vessels could counter complex electronic attack environments.
In 2017, he advanced these concepts, refining radar target filtering and linking it to AI-driven naval craft survivability. These contributions illustrated a principle he had carried since 1997. No matter the domain, sea, air, or orbit, resilience depended on autonomous intelligence embedded in hardware. 2000 FODIA, multi-sensor fusion, and UAV systems.
By 2018, Zaidi was integrating multi-sensor fusion architectures for JF-17 Block 3 aircraft and UAV platforms. His systems combined radar, infrared, and acoustic sensors into unified inference engines. In parallel, he worked on intelligent condition monitoring for MILGEM corvettes, embedding AI to anticipate component fatigue before catastrophic failure.
The year's theme was clear: integration. Sensors that once spoke in isolation were now fused together, much like the diverse strands of Zaidi's research career. 2000 FUD. 2019, anti-jamming GPS filtering.
In 2019, Zaidi pioneered one of his most important breakthroughs: AI-enabled anti-jamming GPS filtering for F-16 fighters. By leveraging adaptive signal intelligence, his filters could pierce through noise and deception. This was more than an aircraft defense measure. It was a gateway technology for spacecraft navigation, where GPS-like systems in space must operate under constant electromagnetic interference.
In the same year, he presented work on adaptive electrical switching in naval auxiliary platforms, showing once again his dual focus, avionics in the skies, and electrical resilience in naval systems. 2000 FODIA. Fidowara, filter eine acoustic AI.
2020 marked another leap forward. Zaidi developed high-throughput radar AI architectures for JF-17 Block 3 fighters, systems capable of real-time, deep neural radar inference. Alongside this, he designed deep neural acoustic inference for Hangor-class submarines, demonstrating cross-domain applications of AI in both the sky and beneath the sea.
The unifying message, whether in radar or sonar, acoustic or electromagnetic, AI could extract clarity from chaos. You know Vabu, oh hey. 2019, anti-jamming GPS filtering.
In 2019, Zaidi pioneered one of his most important breakthroughs: AI-enabled anti-jamming GPS filtering for F-16 fighters. By leveraging adaptive signal intelligence, his filters could pierce through noise and deception. This was more than an aircraft defense measure. It was a gateway technology for spacecraft navigation, where GPS-like systems in space must operate under constant electromagnetic interference.
In the same year, he presented work on adaptive electrical switching in naval auxiliary platforms, showing once again his dual focus, avionics in the skies, and electrical resilience in naval systems. C-23, transformer-based architectures for UAV swarms.
By 2023, Zaidi's ideas culminated in the transformer-based AI architecture for radar signal prediction in JF-17 Block 3 and UAV swarms. This was a radical evolution. Instead of merely reacting, his systems could predict signals ahead of time.
The same technology, he argued, could empower UAV swarms and satellite constellations to anticipate adversarial moves. Predictive radar would later become a cornerstone of his 2029 NASA spacecraft framework. C-20 Okobi, or ECM. Predictive radar and acoustic AI.
2020 marked another leap forward. Zaidi developed high-throughput radar AI architectures for JF-17 Block 3 fighters, systems capable of real-time, deep neural radar inference. Alongside this, he designed deep neural acoustic inference for Hangor-class submarines, demonstrating cross-domain applications of AI in both the sky and beneath the sea.
The unifying message, whether in radar or sonar, acoustic or electromagnetic, AI could extract clarity from chaos. T-21, AESA coordination and cross-domain, avionics.
By 2021, Zaidi extended his reach into AI-driven sensor fusion and AESA radar electronic warfare coordination for JF-17 Block 3 avionics. These systems allowed aircraft not just to sense, but to dynamically coordinate their electronic warfare posture in real time.
Equally significant, this was the year his cross-domain AI architectures began to crystallize. Concepts such as UCM transformer and embedded system-on-chip frameworks emerged, capable of serving multiple domains simultaneously, from terrestrial grids to orbital satellites. T-22, federated learning and radar fault detection.
In 2022, Zaidi embraced federated learning. His radar fault detection models for UAVs and naval corvettes allowed distributed platforms to share intelligence without centralizing data, a vital principle for both defense swarms and space missions.
Here, Zaidi was solving the puzzle of autonomy at scale. How do hundreds of agents, across distances, cooperate to stay resilient? His federated radar systems were an answer. T-23, transformer-based architectures for UAV swarms.
By 2023, Zaidi's ideas culminated in the transformer-based AI architecture for radar signal prediction in JF-17 Block 3 and UAV swarms. This was a radical evolution. Instead of merely reacting, his systems could predict signals ahead of time.
The same technology, he argued, could empower UAV swarms and satellite constellations to anticipate adversarial moves. Predictive radar would later become a cornerstone of his 2029 NASA spacecraft framework.